Welcome to this next video in the playlist on ring theory. In this video what we're going to do is define what is meant by a greatest common divisor. Now before we do this we're going to define some other terms which we're going to need in order to discuss greatest common divisors. Okay, so all the terms that you will see in this video, you will have seen them before and you will be used to them from classical arithmetic in the context of the integers, okay, the ring of integers. What we're going to do in this video is we're going to generalize and go over to just working with a commutative ring, because all of these concepts can be applied to commutative rings. They don't just relate to the ring of integers. Okay, so that's what this video is all about. Okay, so let's get cracking. So we're going to first start off with the definition of what it means to say that an element is a multiple of another element, and what it means to say an element is a divisor of another element. Okay, so let's start off with some commutative ring, capital R. Okay, so throughout this video we're going to be working with a commutative ring. Okay, so here we have our commutative ring, capital R. So this is a set of symbols with an addition and multiplication law defined on them, and those addition and multiplication laws obey all of the axioms that we need to be true for it to be classified as a commutative ring. Okay, right. Now, let's start off with the definition of is a multiple of. So let's take two elements from our commutative ring. So let's take an element A and an element B, which are both from my commutative ring, capital R. Okay, now A can be whatever you like. Okay, so A is truly whatever you like. B can be whatever you like, apart from it can't be one element. So I'm going to curtail what B can be a little bit more than I curtailed what A can be. So I'm going to restrict B down and say that it's not equal to the additive identity. So B can be anything apart from the additive identity. So A can be absolutely anything in this commutative ring. B can be anything, but it can't be the additive identity. So everything except the additive identity. Okay, so now what I'm going to define is what is meant by saying A is a multiple. Okay, so A is a multiple of B. Okay, so I want to define what do I actually mean by this. Okay, so this is the rigorous definition of A being a multiple of B. Okay, so if you say that A is a multiple of B, it means that you know that there exists some other element, which we'll call little x here. So there exists a little x, which is an element of the commutative ring, okay, such that if I multiply little x with B, it gives me A. Okay, so such that A is equal to x times B. So there must be some element within your commutative ring which you can multiply with B to give you A. And that's what it means to say that A is a multiple of B. Okay, so that is what it means to say that A is a multiple of B. That's the definition. Okay, right, so let's try and interpret this a little bit more in terms of the multiplication table for our commutative ring. So let's just draw a little picture here. So I'll draw out my multiplication table for the ring. So this is multiplication. So of course the commutative ring, I'll put every single element of the commutative ring down here. So I'll give every single element of the commutative ring a row in this multiplication table, and I'll just colour in the multiplication table here in green. So I'll give every single element of the ring a row in the multiplication table, and every single element of the ring will have a column in the multiplication table. So what does this criterion really say? Well, if we consider the column corresponding to B here, and you could consider the row, it doesn't matter because we're dealing with a commutative ring, so the row and the column will look very similar. We'll consider the column, however. Okay, so we've got the column corresponding to B here, and now of course all the entries in this column corresponding to B, they will be corresponding to different rows here. Okay, so if you go through all the different entry elements of the ring here and ask what is that element of the ring multiplied by B, okay, so an arbitrary element here, little x, okay, if you're asking what is x multiplied by B, you're just looking for the entry which is the intersection between the row corresponding to the element little x and the column corresponding to the element little b here. Okay, and I'm saying that for some element of the ring it has to be the case that that element of the ring multiplied by B will give you A. So somewhere in the column corresponding to B, there has to lie the element A. So A must appear somewhere in the column of B, and that's what it means for A to be a multiple of B in terms of the multiplication table here. Now, as I say, because multiplication is commutative, the row will look just like the column rotated round a little bit here, okay, rotated round by 90 degrees, okay, so if A appears in the column corresponding to B, it will also appear in the row corresponding to B. So to say that an element little a is a multiple of an element little b, it means that A must appear in the row and the column at least once corresponding to the element B. Okay, and the reason that we had to say B was not equal to 0, I hope you can understand, is that if we look at the row and column corresponding to 0, we just have 0, 0, 0, 0, 0. Okay, so it's silly to look at B equal to 0, because the only thing that's a multiple of 0 is 0 itself. Okay, so you don't apply this when B is equal to 0. Okay, so that's the definition of A is a multiple of B. Okay, so now what I want to do is look at from the opposite point of view. I want to have a look at what the definition of a divisor is. Okay, so it's the exact same condition but from the opposite point of view. So what we can say, if this is true, so if A is a multiple of B, then you can phrase it another way. You can phrase it from the point of view of B, and you can say that B is a divisor of A. Okay, so if A is a multiple of B, you can also say that B is a divisor of A. And saying that B is a divisor of A is exactly this condition as well. It means that there exists some element of the ring which if you multiply it with B, you get A. So it means exactly A is a multiple of B. Okay, it's just stated from the other point of view. So that's what it means to say that one element is a multiple of another element, and another element is one element is a divisor of another element. Okay, right. Now, a bit more notation. If you have an element B which is a divisor of A, there's a way that people love to write this. Okay, number theorists absolutely love this notation. Okay, they like to write B divides A. Okay, so this is a way of writing B is the divisor of A. B divides A is the way that you should read this, and this means exactly this statement up here, that there exists some element of the ring, little x, such that if we multiply that element of the ring with B, you get A. Okay, right, so there's just a little bit more notation. Now there's another way that you can phrase this in terms of ideals, and I just want to show you that because that's going to be helpful when we go on to discuss greatest common divisors. Okay, so if A is a multiple of B, then it means that there exists some element of the ring such that if you multiply that with B, you get A. Okay, indeed, A appears in the column corresponding to B and the row corresponding to B. But the column or row corresponding to B is exactly what we mean by the principal ideal generated by B. Okay, so remember, the principal ideal generated by B is the subset of the ring which contains this element of the ring B here multiplied by absolutely every single element of the ring. So if I write this out, it's the set that contains all things of the form x times B, where x is an element of our commutative ring capital R here. That's the definition of the principal ideal generated by B. So effectively, here's a very literal interpretation of that. You just go down the column or the row, it doesn't matter because we're working with a commutative ring. You go down the column or the row corresponding to B, and you look at all the answers that appear in the column or row corresponding to B. You stick them all into this set, and that's what is the principal ideal generated by B. And that's because you are just going through all the elements of the ring and multiplying them with B, and that corresponds in terms of this picture to just going down here, changing the row that you're working with as you go down all the elements of the ring and asking what does that element multiplied by B give, and then you're looking at the entry in this column corresponding to B here. Okay, what we're really saying then is, if we're saying that A is a multiple of B, we're saying A is in this column, so we're saying that A must be in the principal ideal generated by B. Okay, so that's another way of saying that A is a multiple of B, saying that A must be in the principal ideal generated by B. And there's one final way that people love to put this, because if A is in this principal ideal generated by B, then because the principal ideal generated by B is a principal ideal, is an ideal, it doesn't matter that it's a principal ideal, is an ideal, full stop, it means that all elements of that ideal, if they're multiplied by elements of the larger ring, capital R, will give you an answer back in the ideal. Okay, that's just the definition of an ideal, that it's closed under multiplication. Okay, so that means I can multiply A, this element of this ideal, by whatever element of the ring I like, and the answer will always be in there. So that must mean that the entire principal ideal generated by A is a subset of the principal ideal generated by B. Okay, so as soon as you know that an element is in an ideal, you know that its entire principal ideal generated by that element is in that ideal. Okay, because of the fact that an ideal has to be closed under multiplication by the larger ring. Okay, so this is another way that you can state the condition for A to be a multiple of B. So if A is a multiple of B, then the principal ideal generated by A must be contained in the principal ideal generated by B, and equivalently, if B is a divisor of A, then the principal ideal generated by A must be contained within the principal ideal generated by B. Okay, right, so that's the definition then of multiples and divisors, and you will note here that of course any element is always a multiple of itself, okay, because you can always use 1 as your element of the ring here. Okay, so if B was equal to A here, then you could put in 1 there, and so that would show you that any element was a multiple of itself, and also any element was a divisor of itself. Okay, right, but that's the sort of trivial case. So that's the definition of is a divisor of and is a multiple of. Okay, so those are the rigorous definitions. So now let's go on to the definition of greatest common divisor. Now before we do greatest common divisor, we should do common divisor. Okay, so now we're going to take this up a step. We're going to go a little bit more complicated, and now what we're going to be looking at is something that's a divisor of 2 elements. Okay, so now what I want to do is common divisors so that we can do greatest common divisors. Okay, so common divisors first and then greatest common divisors. Okay, right, so common divisors. So now what we're going to do is pick 2 elements of the ring, and we then want a third element of the ring which is going to divide both of them. And we're going to use the notion that we've got of is a divisor of to define that now. Okay, so let's pick 2 elements from our commutative ring. So let's say we've got A and B, which are both elements of our commutative ring, capital R. Okay, and they can be whatever elements of the ring you like. So I'm not going to restrict them to not being the additive identity now. They can both be the additive identity if you wish. They can be whatever elements of the commutative ring you like. Okay, so a common divisor, which I will now call D, is some element of the ring, capital R, which again will not be the 0 element, so I'll subtract the 0 element. Okay, so remember the divisor always is not the 0 element. Okay, so this is our divisor, this is effectively equivalent to what B was before, so I'm saying it's not going to be equal to the 0 element. Okay, and this common divisor, the definition of a common divisor then, is that it must divide both A and B. Okay, so if it's a common divisor, D must divide A and D must divide B. So a common divisor of these 2 elements, A and B here, is something that divides both of them. Okay, now if D divides both of them, then both A and B can be written as multiples of D. Okay, so some element of the ring can multiply by D to give A, and some other element of the ring can multiply by D to give B. Okay, so what I can now say is that both A and B are elements of the principal ideal generated by D. Okay, so hopefully you should be used to that by now. If these are going to be D multiplied by some element of the ring in both cases, then they're of course going to be in the principal ideal generated by D. Okay, now, if A and B are both in the principal ideal generated by D, then what we can say is that the ideal generated by A and B, okay, and this is a new concept, I have not introduced you to this so far in the playlist on ring theory, so I will go through this in a little bit more detail. So what I can say is that the ideal generated by A and B, so you should read this as the ideal generated by A and B, and as we'll see, we will explore this in a bit more detail in just a moment. This is going to be the smallest ideal that can contain A and B, so the ideal generated by A and B, and it's a generalization really of the concept of a principal ideal. Okay, so that's what this notation, curly brackets and then A comma B like that means. The ideal generated by A and B, the smallest ideal that contains A and B in the commutative ring capital R, must be completely contained within the ideal D. Okay, so if this is the smallest ideal that A and B can possibly be contained in, then if D contains both of them, it must contain all the elements in here, as we'll see. Okay, so before we go any further then, let's explore this ideal generated by A and B. Okay, so rather than trying to motivate this and then define it, I'm just going to go straight in and define it, and then we'll see the motivation behind it. I think that's the best way to do this. Okay, so the ideal generated by A and B then, it is going to be the subset of our commutative ring that consists of all things of the form R1 times A plus R2 times B. Okay, and I've got two things to show you. Firstly, I want to show you that this is an ideal, and secondly, I want to show you that it's the smallest possible ideal that can contain A and B. Okay, so this is going to be the set of all things of the form R1 times A plus R2 times B, where of course the multiplication and the addition is done in our commutative ring capital R, and R1 and R2 are elements of the ring capital R. Okay, right, so firstly what I want to show you is that any ideal that contains A and B is going to have to contain everything of this form, okay? And then what I want to show you is that this actually is an ideal, and therefore we can conclude that it's the smallest ideal that can possibly contain A and B, because as I say, every ideal that contains A and B must contain everything of this form. Okay, so why is any ideal that contains A and B going to have to contain all of these things? Well, because an ideal is closed under multiplication, that means that any ideal that contains A must contain all multiples of A. Okay, so it must contain all things of the form R1 times A, where R1 is an element of the ring. Because the ideal is closed under multiplication again, any ideal that contains B must contain all multiples of B, so it must contain all things of the form R2 times B, where R2 is an element of the ring. Okay, and because it's an additive subgroup and therefore closed under addition, then any multiple of A in this way, plus any multiple of B, must also be an element of the ideal. Okay, so any ideal that contains A and B has to contain all things of this form. Okay, so we've agreed that now. So if we can show that this subset alone of all things of that form is an ideal, then we can agree that it's the smallest possible ideal that can contain A and B, okay, because as I say, every ideal that contains A and B has to contain that, so there can't possibly be a smaller one, because if there was a smaller one it would not contain one of these elements and therefore it wouldn't be an ideal. Okay, so that's our strategy. So now let's actually prove that this is an ideal therefore. Okay, and what we want to prove to do that is we need to prove that it's an additive subgroup, that's criterion number 1, and secondly we need to prove that it's closed under multiplication. Okay, so this is all very easy, so let's start off with additive subgroup. So remember, whenever we want to show that a subset is an additive subgroup, all we need to worry about is axiom number 1, closure, axiom number 3, the additive identity, and axiom number 4, additive inverses. We don't need to worry about associativity, and we certainly don't need to worry about commutativity. They come naturally to any subset with the restricted composition laws from the ring. Okay, so let's firstly work on closure then. So what I want to show is if I take two elements from this subset and add them together, I will end up with another element in this subset. So let's take one element. So one element will look like this, or be of this form, R1 times A plus R2 times B here. So here's my first element, and I'm going to add it to, so this is one element from the subset, and I'm going to add it to another element which I'll call R1 bar times A plus R2 bar times B. Okay, so the R1 bar and R2 bar are not the same as R1 and R2, obviously. Okay, so I've just taken one arbitrary element of this subset, I've taken another arbitrary element of this subset, and I want to prove that if I add them together, I get something else that's in this subset. Okay, now of course this addition is defined, because in the larger ring it's defined. I just have to make sure that when I do add these together, I don't get something that's outside of this subset in the ring capital R. Okay, so how can I do this? Well, I can use the fact that addition obeys associativity and commutativity to just manipulate this as I please. So what I'll do is I'll bring this one over here next to this one, okay, and I'll bring these two next to each other. That's fine because addition obeys associativity and commutativity, so we can manipulate it as we intuitively want to. And then what I'm going to do is factor out the a's, okay? So I'll do this all in one step. So we'll end up with R1 plus R1 bar times A plus R2 plus R2 bar times B. Okay, now I know I haven't done that to full rigour, okay, but I hope that your intuition with the way that rings works is now good enough that you're happy with me doing that. Okay, you could go through this fully rigorously and say, okay, using associativity of addition we can do this, and then using commutativity of addition we can do this, and then using right distributivity we can factor it into this. Okay, but I hope I don't need to do that because your intuition for rings is growing. Okay, so now I claim that we have something that is going to be in this subset, because look, R1 plus R1 bar, that's just going to be some element of the ring, okay? And R2 plus R2 bar, that's also just going to be some element of the ring. So I do now have something of the form, an element of the ring multiplied by A plus an element of the ring multiplied by B. Okay, and that's the form that things in here are all conforming to. So this addition, the sum of these two elements, does conform to the criteria for being in this subset. So indeed, when you add two elements of this subset together, you will end up with another element of the subset. Okay, so that's very nice. Now let's do axiom number 3 then. Okay, so the additive identity. So we need to make sure that the additive identity from our larger ring is going to be in here. Now, hopefully that should be pretty obvious. R1 and R2 are allowed to vary over any elements of the ring. So let them both equal the additive identity. So if I put in R1 is equal to the additive identity and R2 is equal to the additive identity, of course when I multiply anything with the additive identity I get the additive identity back again. So both of these will turn into the additive identity, and then I'll add two lots of the additive identity together to get the additive identity back again. So the additive identity is going to end up being put into this set basically. Okay, so end of proof, 0 is going to end up being in this set, the ideal generated by A and B. Okay, so that's fine. Now let's do axiom number 4, which is additive inverses. So what I want to prove is that if I take some arbitrary element of my ideal generated by A and B, so let's say an arbitrary element looks like this, R1 times A plus R2 times B, where R1 and R2 are elements of the ring capital R, so this is some arbitrary element of the ideal generated by A and B. What I want to prove is that it has an additive inverse in this ideal generated by A and B. Okay, so I claim that the additive inverse is just going to be this thing. Okay, the thing of the form, the additive inverse of R1 times A plus the additive inverse of R2 times B. So you give me anything that's in this ideal generated by A and B. I will find the R1 and R2 here, then I'll just take their additive inverses in the ring, and I'll then construct this element, which I hope we both agree is going to be in the ideal generated by A and B, and I claim that this element is going to be the additive inverse of this element up here. Okay, and why will that be the case? Well, we know how elements of this form add together. They'll add together by getting the things that are in front of A added together, and then the things that are in front of B added together, and of course when R1 adds to negative R1 we'll get the additive identity here, and when R2 adds to negative R2 we'll get the additive identity here, so of course we'll end up with the additive identity. Okay, so that's why additive inverses are going to exist within this subset. Okay, and then we don't need to worry about axiom number 5, commutativity, that comes naturally. So this subset then now does obey the criteria for being an additive subgroup. Okay, so that's excellent. Now we need to prove is criterion number 2 of an ideal, which is that it's closed under multiplication by the larger ring. So what I want to prove is that if I take an arbitrary element, so let's again have an arbitrary element, and I'll just move this up a bit. So let's take an arbitrary element, R1 times A plus R2 times B. So this is some arbitrary element from the ideal generated by A and B. What I want to prove is that if I multiply this by an arbitrary element of the ring, so for all, let's say R is an element of the ring capital R, okay, I want to prove that if I multiply these two things together, I end up with something that's back in the ideal generated by A and B. Okay, so if I multiply R with this element R1 times A plus R2 times B, okay, I want to show that I get something back in here. So I want to show that I end up with something of the form something in the ring times A plus something in the ring times B. Okay, well, let's just apply distributivity here. So what we'll end up applying left distributivity, we'll get R times R1 times A to leave the brackets in, plus R times R2 times B, again leaving the brackets in. And now we'll apply multiplicative associativity to reassociate the brackets. So we'll put the brackets instead around R times R1 here, and then have it multiplied by A, and then we'll put the brackets in the different place here as well. So we'll have R times R2, and then that product will be multiplied by B here. Okay, so of course, sitting in front of our eyes now, we've got an element of the ring multiplied by A, plus some element of the ring multiplied by B, which of course is going to be an element of our ideal generated by A and B. Okay, so this is going to be in the ideal generated by A and B. Okay, so this subset of all of the elements of this form, so you go through and you let R1 and R2 vary over every single element of the ring. You take every possible combination R1 and R2 that you can possibly come up with from the ring, construct the answer to this thing, R1 times A plus R2 times B, get all of those answers, stick them all into this set, okay, and that set is actually going to end up being an ideal. Okay, and we've agreed that all the things that are in that set, if you've got an ideal that contains A and B, all of those elements have to be in there. So this has to be the smallest possible ideal that contains both A and B. Okay, so that is what is meant by the ideal generated by A and B. It is truly the smallest ideal that contains A and B. Okay, so if we have a common divisor, so back to common divisors, if we do have a common divisor D, which divides both A and it divides B, then we know that A and B must be in the principal ideal generated by D, so that therefore implies that this smallest ideal that possibly contains A and B must be completely contained within the principal ideal generated by D. Okay, so that gives us good intuition with regards to common divisors. We'll take a break there, and in the next video what we'll move on to is the concept of a greatest common divisor.